Hello and welcome to Dijkstra Academy. Today we'll be talking about graphs and algorithms with them and displaying them. The code that we will take a look at today is inspired by the book of Ala Hamis that you see here, and the book is called Optimization Algorithms, and mainly I'm talking about chapter 3. Here, Introduction to Graphs, we'll be taking a look mainly at libraries and some of the examples shown here. Of course, I'm going to make them more interesting for me, but you'll be able to recognize them. Okay, so what did we do last? We were showing undirected, directed, multigraph, acyclic graph, hypergraph, and weighted graph. Are we going to use something of this? The answer is pretty much we're gonna use the fact that we have edges and points, and everything in a graph can, once it is mapped, it can be used, but we'll be using completely different libraries. So let's start and let's run them. So shut up and shut up please are actually suppressing warnings from a lot of libraries in pandas, so that's better. Then we have pandas, Matplotlib, NumPy, and these ones are like the standard one that we usually put. Then we get with NetworkX, and the idea of NetworkX is that it provides tool for creating and analyzing complex graphs. Then we have OSMnx, which downloads and analyzes street networks and geospatial data from OpenStreetMap. And then we have Folium that builds interactive leaflet maps directly in Python, perfect for visualizing geographic area. So let's start. First, just some spoilers here. If you stay up to the end of the video, you would see some code that actually results like this with nodes and edges. Pretty much you see dots and lines. Lines are edges, dots are nodes. And we'll see how to find the shortest route for walking and for driving between origin and destination, and how do we plot it with plot graph route. How does it look on a specific map from open free maps, and then how the whole route looks. And additionally we'll see some fancy pop-ups. How do they look here, and how the map of Sofia, for example, looks with a radius of 5,000 between our dots. So let's watch further. As I'm living currently in Sofia, Bulgaria, I'll geocode two famous locations in Sofia, and they'll be called start point, and they will be called endpoint. So the start point is called Vasil Levski monument. I'll use it like this. And I'll write, of course, Sofia, Bulgaria. And the endpoint is a church in the area. Not so much in the area, it's like 2 kilometers from there, but it's a famous one. And I'll write church. Okay, so we just entered our start point name. And for some reason it doesn't want to print. Let me restart. Yeah, perfect, I have it. So let's try to geocode it. So OX is actually OSMnx. Dot geocode. start point name. And it doesn't return something, but we can say that it's a start point geocode equaling like this. And somehow it cannot find it. It's not okay. I would say let's try with the endpoint. And the endpoint is okay, but we need the start point as well. Could be that I use monument. Yeah, and we have it. So the word here is we should be using monument, not the Bulgarian word for it. Sometimes OpenMap works perfectly, but that's not the important thing. So let's continue. Endpoint geocode, and we have endpoint name. And what we can do is the following. Now we have the start point and the end point. We can say, just to check that actually there would be something between these points, we can try to search for it in Google, saying from start point geocode 0, which should return us the latitude like that, and then start point geocode 1, 2, endpoint geocode 0, endpoint geocode, just showing something. If string is not allowed, now it is allowed. And the idea is that if we Google for this and we say search Google, and somehow we fix a bit this, we will see that this is what Google returns from square of Vasil Levski to the address of the church. This is what we will be trying to find today when we will be working. Yeah. Perfect. So let's generate a street network graph around the monument. And in order to generate this street network graph, we need a central point. And this central point would be the equal between the geocode and, not the equal, the average between the geocode start and geocode end, both for latitude and for longitude. So it should be something like this, divided by 2, and then this plus that divided by 2, of course I said. So latitude here, and endpoint should be here as well, so like this and like that. Great. Okay, and it should be like a tuple, so comma, and then endpoint geocode 1, yeah. The idea is to get the average of the two. So this is the central point. Let's see how it will work. So central point is 42 something. Yes, it is. Looks like 42, between 69 and 68. It is something. Yes. And then 23, 33. It is average. Yes, great. So we continue and we try to get the graph from point where we would be saying that we want all drivable roads between 1500 meters of this location. So let's do it. So graph equals ox dot graph from point, and we say center point. The distance is in meters, so we say 1000 meters, and the network type is drive. Fair enough. I'll put this one as a variable so I can change it later. Type of network drive. Yeah, network type equals type of network, and center point is not defined. Yeah, makes sense. I was thinking about central perk, so I called it this way. Yes, and now I have a graph. Let's see if I call it here, what I will get. I'll get an object. So the question is, how do we plot this object into something that actually starts making sense? So we will use the ox.plot graph. Makes absolute sense. And we will say graph. Would it return something? Yes. Just that, return something. Perfect. And what if we want to change something? Let's say background color, for example. Background color, I want to make it yellow. What else? Each line width would be 0.1. Node size 50, and fixed size 10 by 10 is okay. Okay, and now I see that edge color should be also black, so it makes sense. And a comma, and then node color equals black as well, and no comma there. Yeah, perfect. And we have something here. And if we say that each lines are 0.1 and are too tiny, we can make it like 1. Yeah, perfect. So we should go somewhere from here to somewhere here on our map, and our central point is somewhere here. So far so good. Let's find a way to mark the nearest node. These points here are called nodes, and the lines are called edges into graph theory. So we want the nearest node on the map to our points, the start and the end point. So this would be where we would be starting, and after finding it, we will actually start running. Okay, so how do we do it? We call origin node and destination node. Yes. So ox distance nearest nodes. Nearest nodes is perfect. We pass the graph, the start point geocode, the end. Okay. In this case, it's, let's say, shift tab. So this is what we are doing. X and then Y. We first pass the X first, then we pass the Y. And this is something to remember, that it's first the 1, then the 0. Yeah. Pretty much the same with destination node, but it will be endpoint geocode, endpoint geocode. Great. And let's plot it. How do we plot it? Let's think about it. Something like this should do the graph. Yeah. When we do this in Python, fig, ax equals, it means that we are assigning two things to value. For example, let me see. Let me show. For example, a, b equals 51, 54, 52. Then if we say a equals 51 and b equals 52. That's the idea. So fig ax is going to receive two values. So ox plot graph, and we pass, of course, the graph. Then pretty much everything from here. It will not be yellow, it would be black. And the edge colors would be white and white. Perfect. So let's get the coordinates of the nodes. So origin xy equals, we'll be making the tuple, so graph dot nodes origin node and it will be using x, and then origin node y, something like this. And then we have the destination xy. I'll copy here, so we have destination node yeah, this should be enough. And now let's make it a bit more interesting. It's complaining, but it will be working at the end, I'm pretty sure, or at least I hope so. No, actually, it shouldn't be like this. It should be show equals false and close is false as well. Node size, age. Of course, we are missing the graph. That's why it says that we are missing the G, one per positional argument. Yeah, okay, we have it. It looks okay, we just don't see the destination and the origin here. So we have to plot them, and let's see, for example, if we have AX are the axis. Great. So we'll use AS scatter. Origin XY is 80, color red, label equaling origin, and Z order will be 3. Let's see, POT show. Yeah, it is here. And what about the other one? Label destination. Z order 3 as well. Color would be green. And it will not be origin, but it will be destination XY. We try, and this is it. These are the edges that are closest to our destination points. What else can we say? We can put some legend and title. AX legend, yeah, AX legend is a good idea. And of course it's always there's a mistake. Note, okay, quite okay with this one. We can put a title, but probably later. Okay, so what do we do now? We need to use Dijkstra's algorithm. I have another video for Dijkstra's algorithm showing how it works. So pretty much we have to come from here to there. And some of these streets are actually one-way streets. This is usually the case in any center city, in any capital city of Europe. Yeah, the center is really usually with one-way streets. So in this case, it will not be like the Dijkstra's algorithm as it seems like from here, but it would be different because, as I said, they are not one-way streets. Yes, so let's use NetworkX that has already implemented Dijkstra's algorithm with shortest path that we simply have to call it. It looks like this. So we say route, and it is NX shortest path. We use the graph that we just created. Then origin node, destination node, weight will be the length, and the method is Dijkstra. How do we write it like this? Yeah, let's see. Route, this it simply returns us some numbers, but the NX library knows how to make a route out of these numbers, pretty much. And we can even calculate the route length in meters, and it should be NX shortest path length. And let's use the same. Graph, original, destination, north, length, yeah. And shortest. Yeah, the meter is around, the length is around 1 kilometer, 680 meters. Okay, and now let's plot this route. So, using the OX plot graph route, why I don't see it. Okay, here, and we can say graph, we can say route. This should be enough. Yeah, it is enough. We have it, graph and route, great, nothing more. We can start asking for other stuff, but they are not that meaningful. Yeah, and it's written in red, why not? Perfect, works. So let's put Folium into the whole party. So we can create an interactive Folium map to visualize everything a bit better. I mean, it will not be only edges and points that had names, but I just forgot them. It would be like general cool map on which we can start drawing. So let's do it, and we'll use what was used in the book. From what I remember, the word m as a single variable, and we'll say Folium dot map, and we'll say location is the center point. Then we'll say zoom start, 15 is a good one. tiles, something like Kartod Bipiozitron, great. Then zoom control. First try with false, you can try with true. And dragging would be also false. Let's try it. Yeah. M is not defined. N is not defined, yeah. They're close to the keyboard. Okay, not that bad. I got a map of the world. So I need to put something like a scroll view zoom. False. Oh, location. This is what I meant. Yeah. Okay. So we were looking from road from here to somewhere here, and let's find our way to do it. So as you see this map, we only see the roads, but we do not see the edges and the lines and the dots. So let's find a way to actually put them into a map. And first we need to convert the graph into a geodata frame of edges, which looks like this. Edges geodata frame equals OX graph to GDFS, and we say okay, graph without nodes and edges. Okay, so nodes and edges are the two things that we care about when we talk about graph. And let's see, we got a list that actually shows a lot of information, like whether it's a bridge, whether it's a junction, whether it's a tunnel, whether it is a one-way or reversed, the length of the road, and the other 768 rows that we care about. So if you remember, when we were looking at here route here, then each route is something to do with these numbers here. For example, this one is most probably the ID that we cared about. Yeah. So, of course, not all the edges and nodes in the map here are the ones here. Only the one that we cared about. For example, this area of the map is not pasted, but that's for good, it saves us time. Okay, let's find a way now to iterate over each edge that is a street segment, extract the geometry and plot it on a Folium map as a gray line. Yes. So it will give us a background of all those streets before plotting the shortest path. Yeah, it will make sense. So for underscore row in edges gdf dot the rows, just if you know what this underscore is, the reason to exist is that we only care about the row, but it's a tuple, whatever is into this thing here. So we kind of tell him, like, the first one I don't care about, I care about the second, but I have to call the first one as well. Yeah. So the coordinates are let long for long, and then let in row geometry dot chords. Okay, so Folium dot polyline coordinates, the color I said white, light gray, which is this one, and we have weight equals 1 and opacity equaling 0.5. Okay, add to M, and M is this one here, if you have forgotten. Okay, didn't like something. I think the 8s are too many. 1, 2, 3, 4, 5, 6. I don't know, it's the equal sign. And Folium polyline is something that shouldn't be like this. Yeah, it's fancy camel case. Okay, now it looks okay. And now let's extract the latitude and the longitude coordinates of each node of the shortest road. And we can do even further, and we can draw the blue polyline on this map. So let's try it. Route coordinates equals graph nodes node, and we care about the y. Yeah, first the y then the x. It's a bit strange, but yeah, whatever. Not up to us to say. As far as we're using a library for kind of free, it's okay. I didn't close something. Let me see which one I didn't close. Notes, something like this. On line 1, closing parentheses. Ah yeah, we have this one, so it means that we should be having it like this. And then like that. And then like that and that and that. And node is not defined. Of course it's not, because we should define it like this: for node in nodes in route. Yeah, this is something. Okay, so we have the route coordinates. Great. I would say it's kind of okay, I guess. And yeah, what should we do now? Let's take a look how the M looks. And this is what we wanted to see. Ta-da! We have the gray things that we have added on our edge. So what we are actually interested in really is the road from here to somewhere here. Yeah, that's great. And let's make it a bit more interesting. What does it mean? We can say, we can even put the road with Folium, and it's actually one-liner. So it's like this: polyline, route coordinates. The color would be blue, and that's enough. And we say add to M. Ta-da! And we have it. So now let's make it a bit more interesting. Let's put some markers. So we are going to put a marker at the start, marker at the end, and a marker in the middle. Why do we need a marker in the middle? Just because we can do it. So, and we need to show how we do stuff with Folium, so to say. So let's put the marker in the middle. Folium.marker. Location is the middle center point. And then we have the icon, and in Folium there are plenty of icons, like anything you can think of. For example, we'll just define the color. For this one I'll put a flag. And prefix would be FA. And there will be even a pop-up. And I'll use a link to Vidus Academy. Just for the fun of it. Yeah, and now close the tag. Will it work? Let's see. Okay, syntax error, really? Yeah, no comma here. Now it works. And the good thing is that actually we didn't do anything. We have to say add to m. Yes. And now when we call m, marker location must be assigned with added directly to the map. Okay, something is not okay. Yeah, of course it gives the same. So location, yeah, mistakes happen all the time. Marker location, yeah, okay, so location, we have it. This center point. Then the icon. Yeah, true. So how did I resolve the whole thing? Pretty much some kind of a reset was needed here. I mean, I read 10 as a zoom start, and then our thing was perfect. Then I went here and I said, okay, I said 15 initially, so I want my 15. And it actually works. So I'll consider this a technical error. And as a bonus, I have prepared 2 other markers. And even the one here, my block, Academy, can even make it like this. So this is how it starts. From here you can see the monument Vasil, Levski, Sofia, Bulgaria, ending in Sveti, Sedmochislenitsi church, Sofia, Bulgaria, and the middle between them. You can take a look at my block, and my block actually works. So, I mean, it works from Jupyter Notebook. That's the interesting part. So pretty much this is what we have, and let's see what we can do with the whole thing. Pretty much I'm thinking let's show some code if you want to like to impress someone really with just 4 or 5 lines of code. You can do the following. You can say the place name. In our case it will be the start point name, which you can change somewhere here. And once you have it, you say the distance in meters. So in our case it will be 3 kilometers. You can say the graph is the OX graph from address, and it could be place name. The distance would be the distance, and the network type would be whatever I have set here, type of network. Yeah, sorry for the quick scroll. And then we have OX plot graph, and we have graph and the figure size. It should be 10 by 10. Great. Fixed size equals 10 by 10. And this is pretty much the map of Sofia with dots and lines, the dots being the intersections and the lines being the roads. So far so good. Let's summarize what we have. First, we import the needed libraries. We select the type of network, set a start point name that is actually working to something, create start point geocode. If we go this into Google, we'll find our thing. Just remove the parentheses because Google doesn't like them, I guess. Then we have the center point and our graph. And this is the first plot that actually centers our graph. It's black and yellow, just because we can do it. Then we have the origin node, the destination node, and the figures. And here we plot our origin and destination. They look nice. Then we have to find a way to plot the route. This is how the route looks. Just numbers, but these numbers actually mean something, and in our case we have it great. Then we use the Folium map, and this is the Folium map itself from free maps, and we don't like it because we don't see edges and nodes here explicitly. Edges are the streets, nodes are the dots, so we write them ourselves with gray color. So what we can do is like that. And now here, if we see the map, you would see the polyline for the route coordinator and the gray over the standard roads, which is good. And then we put some markers, and here on the markers we see whatever we have asked for, a pop-up. That actually works in Jupyter Notebook, and that's great. So next is place name and plotting the graph just as a bonus of, let's say, 5,000 meters around the central place. It would be interesting, and I have decided to plot it once more just because we can do it. This is how it looks. What we can do as a goodbye, just showing off, is we can change the type of network from drive to walk and see how it changes everything, or what exactly is changed. The dots are way more, because if you're walking, then the intersections are obviously more, and that's interesting. Also, the shortest road is completely different. It looks like a straight line because you don't have to care about one-way streets when you walk. And pretty much that's all from me for today. I hope you enjoyed the video, and I hope you have a wonderful day. Goodbye.